Beyond basic synchronized blocks, Java provides several mechanisms for thread coordination. Understanding volatile, wait notify, deadlocks, and explicit locks gives us the tools to handle complex concurrency scenarios. The volatile keyword. Volatile is a lighter weight synchronization mechanism that ensures visibility without mutual exclusion. When a variable is declared volatile, every read sees the most recent write by any thread. First, we can see one example like the problem without volatile keyword. Okay. And if we don't put here volatile, then our JVM is free to optimize this method, okay, or block. If we use this method like again and again, then our core engine of JVM, JIT, just in time compiler, hoist this one, okay. So we can see this one with one example, okay. So we can understand one thing, that is JIT compiler. So this is just in time compiler, okay. And this is our core component of JVM's runtime execution engine. So when we start our Java application, our JVM interprets bytecode line by line, which is slow. So as our application runs, our JVM tracks code execution frequencies like hotspots, we can say. And in this one, you can see like this method is called again and again, right? So when any method or loop is executed many times, then our JIT comes in, okay? Our JIT compiles this bytecode directly into high performance native machine code. We can say like assembly instructions, and it can do some optimizations. So we can understand this one with one example. We can remove all these things. Okay, and we can create here one, let's say, variable private boolean running equals to true, okay. And now here we can create one method, that is private void run loop, and while running we can print anything, okay. Maybe we can do something run loop, okay, and we can initialize here anything, that's fine, okay. And while we are running this one, we can increase that. And now we can create another thing, that is stop loop, okay, running equals to false, and we can print one condition just for logging purpose. And then in our main method, we can create one instance. So let's create one concurrency practice CP equals to new concurrency practice. Okay, now we can create here some threads. Let's call this worker, okay. So we are getting one suggestion. Maybe we can take this one, and here instead of default name, we can put here anything like worker, and let's make this one here thread, okay. Also we can start here another one, that will be our thread. Let's call this one stopper, okay. We can pass here lambda, that's fine, but we can also do here method reference like we did above. So CP stop loop, okay, like that. And then now we can also start this one, okay. And we can like put here any time, let's say 5 seconds, all right. Okay, and after that we can check this one. If worker.is alive, we can print something. And now also we can do like system.exit1, that's fine, we can put here 0. Okay, so now you might be thinking that we are checking here, right? We are calling this run loop from our worker thread and stop loop from our stopper thread. And stop loop will update our running variable, okay, to false to stop this loop, right? But we know that our JVM will optimize this loop because this one will be running like many times. So what JVM will do, or what JIT will do here, it will not check like while running, it will do something like if running, okay, one time. So this will check only one time. So what our JIT will do, it will check only one time, right? And then it will do something like this and also something like this. Okay, and here it will do something like this while true. So we will get not this one, we will get something like this. Okay, and our JIT will check this one only one time. And now our JIT updated this code, okay, for optimization. Our this loop will never end. Okay, right now you are thinking that after our this stopper thread update this one, or this loop will end, but this will not end. Okay, this is one optimization. And if you want to check this one, then we can also do that. We can run here, running. Okay, so you can see we got running. Okay, so let's run this one in our terminal. So this called and still running. So you can see we are not getting this statement, right? Worker thread is still alive because we are not triggering infinite loop here. And that is because if you can see here in this while loop, we are doing this printing statement. Okay, and this one is synchronized internally. If you click on this one, println, then you will find this one. Okay, so here we are using synchronized, and this is interfering with our of our JIT optimization. So if you remove this line, then this time we will get infinite loop. Okay, we can clear this, and also we can run this one here directly. Okay, so you can see. Okay, so after 5 seconds, we got this line. Worker thread is still alive. So that means our stopper thread updated this one, right? Running to false, but our this worker thread didn't take that updated value. Okay, so this is one problem. And if we use here volatile, then this time we will see this one stop loop. Then we will also see, like here we can put else worker thread is dead. And if we run this one, and now we don't have to wait for even 5 seconds. Okay, because the moment our stopper thread updated this one, our worker thread read that updated value here because of this volatile keyword. Okay, and it stopped executing further. So this is the one thing, like practical example of volatile keyword, and you will see this one in many places in our JDK. Okay, now we can proceed further. Without volatile, run method might cache running in a CPU register. Changes made by stop might never be seen. Okay, now what volatile guarantees? Visibility, reads, see latest, writes. Volatile does not provide atomicity. Compound operations still race. Ordering prevents reordering around volatile. Lightweight, no locking overhead. Thread coordination, can't wait and notify. We will see these two methods. Okay. Mutual exclusion, we will not get from volatile. Critical limitation, volatile doesn't make compound operations atomic. If you do this one, still not thread safe. When to use volatile? Simple flags, okay, variables written by one thread, read by others. Okay, this one is important, written by only one thread. Volatile versus synchronized. Use volatile when only one thread writes, multiple threads read. Use synchronized when multiple threads write. Okay, we have compound operations, check, then act. Read, modify, write kind of chain we have. We need mutual exclusion. We need to coordinate multiple variables together. Okay, we can use volatile. We want minimal overhead. We need visibility, but not mutual exclusion. Now next thing is thread communication, wait and notify. Sometimes threads need to coordinate. One thread waits for a condition that another thread will establish. So our wait notify mechanism enables this coordination. So for wait method, this one releases the lock, suspends the thread until notified. Wait timeout, same as wait, but wakes up after timeout if not notified. Notify wakes up one arbitrary thread waiting on this lock. Notify all wakes up all threads waiting on this lock. Critical rule, these methods must be called while holding the object's lock, okay, inside our synchronized method or block. Okay, so we can see these things with one example, producer consumer pattern. The classic example of wait and notify, producers add items to a buffer, consumers remove them. When the buffer is full, producers wait, and when empty, consumers wait. Okay. The key thing to understand, wait temporarily releases the lock. It's called inside. This is what makes the whole pattern work. Without releasing the lock, no other thread could ever enter a synchronized method on the same object. Okay, and nobody could ever call notify. When the thread is notified, it reacquires the lock before continuing. So let's say we have one class, bounded buffer. Here we have this queue of any type we can provide. New linked list, that's fine. Capacity we have 1. Okay, so we want to fill this queue like producer as producer up to this capacity. And when our queue is full, then our consumer can start removing elements. And when our capacity is 0, then we can start adding again. Okay, producing again. Then we have here one constructor. Okay, so this is one that we need to understand. Synchronized void put throws interrupted exception, that's fine. So while queue.size equals to this one, we have to wait. And like here we are using wait, so we will release locks, okay, of this object queue. All right, releases the lock on this instance because this one is not static. So we have to acquire the like this lock which is from instance of this class. And this is also very important that this lock also hold these locks as well. Okay, thread sleeps until notified, reacquires the lock before returning. So queue.add, we can add this one, notify all, wake up consumers waiting for items. Okay, and take. So synchronized throws interrupted exception while queue is empty. So we have to wait now. Okay, and then we can remove this one, notify all, return item. Wake up producers waiting for space. Okay, so wait, notify all, wait, notify all. So this is producer and then consumer kind of thing. Okay, so you can try this example, that's fine. Now why the while loop? Always use while, never if. Wrong, can miss the condition. If queue dot is empty, then wait. So always use this one, rechecks after waking. A thread can wake up without being notified, or the condition might change between notification and acquiring the lock. Always recheck the condition. Now, what is the difference between notify and notify all? Notify wakes one arbitrary waiting thread. Okay, notify all wakes all waiting threads. And then again, they will acquire lock one by one. More efficient if only one can proceed. Safer, correct thread is guaranteed to wake. Risk wrong thread wakes, others starve. Thundering herd, okay, all wake, most pre-wait. Fragmentation, this one, unless we have a specific reason to use notify and fully understand the implications. Okay. Now, next thing, which is very important, deadlock. A deadlock occurs when 2 or more threads are blocked forever, each waiting for a resource held by another. It's a permanent state. The program hangs with no way to recover. So let's understand this one. Thread A acquires lock 1. Okay, needs both lock 1 and lock 2 to proceed. It acquires lock 1 first. and thread B acquires lock 2. Thread B also needs both locks, but acquires lock 2 first. So thread A waits for lock 2, thread B waits for lock 1, and we have here deadlock. So both threads wait forever. Neither can release their lock because they are blocked waiting for the other. Okay. We have here deadlock condition. Maybe we can copy this one. Okay. Or maybe we have one example, right? We can see here as well. But for now, we can remove these things. Pattern counter we have here. In this one, we don't have. So we can remove this one. Okay, here we have two objects, right? So we can remove this thing. Okay, and we can do some changes here to get that lock. So we are acquiring here lock, that's fine. We are increasing this one. We can just so we are acquiring here lock. Then we can print here something, incrementing count, or maybe acquiring lock. Okay. And then here we can see we can do something like try thread.sleep just for 100 milliseconds, that's fine. Okay. And we know that this will throw interpret exception, so we have to capture that. And after that we can acquire synchronized log 2. Okay. And here we can do count plus plus, also count 2 plus plus. Okay. And we can print here anything, acquired log 2 and log. Okay. So we can see. Okay. And same thing we can do here as well in increment 2. So we can acquire this one first, and now here we can print. Now here we can do try catch. Okay. And after that we can ask for lock. Okay. And acquired lock and lock 2. And now what we can do, we can call these two methods from different threads. Okay. So now you can see we are getting one suggestion, that is better counter, like that. Okay. So we can see, we can start, we can join. And now if we run this one, then you will see, click here, rerun. And now you can see we got this one option, dump threads. So we can take from here as well, or we can from terminal by control and then backslash. So click on this one and you will see we got one dump. Our IntelliJ will also show like we have deadlock condition here. We have this dump, and if you come here, then you can see we log this one and we are waiting for this one. So like this one is same. Focus on these last two letters. Here we are logging A8 and we are waiting for B8. And if you come here in thread 1, we logged this one B8 and we are waiting for this one. Okay. So this one is deadlock condition. Okay. Now we can proceed. Preventing deadlock. So 4 conditions must all be true for deadlock to occur. Okay. And we can break any one to prevent it. First one is mutual exclusion. We can use lock-free algorithms, immutable data, hold and wait, acquire all locks at once, or release before acquiring new ones. No preemption. Use try lock with timeout. Give up if can't acquire. Okay. Circular wait. Always acquire locks in the same global order. Lock ordering, the most practical solution. Always acquire locks in consistent order. So first, then second, okay, like that. So if first one already acquired, then any thread that need to acquire like second, then that thread must acquire first, like this one first. So we will not get deadlock in that case. Now next thing is Reentrant Lock, explicit locking. Java.util.concurrent.locks.reentrant.lock provides the same functionality as synchronized with additional features. Let's say we have this class counter, and so we can create here one reentrant lock object, and now here we can lock this one. Then in finally, like in try lock, we can do something, and in finally we can unlock this one. Okay. So with synchronized keyword, we have seen that our lock will be released even if we got exception, right? But with reentrant lock, we must explicitly unlock that one. So always unlock in finally block. This one is very critical. Okay, now why we use reentrant lock over synchronized? So we have some advantages. First, timed lock attempts. Try to acquire a lock with a timeout instead of waiting forever, like this one. Okay, lock.try lock, and like this one is amount and this one is its unit. So this try lock returns immediately true if our lock was acquired and false if not. So no blocking. Okay, couldn't acquire lock, handle gracefully. So here we will wait 1 second, and if we don't provide here any time, then we will return immediately. Okay, in this case, so here we will wait for 1 second to get lock. Now next one we have interruptible locking. Waiting threads can be interrupted instead of blocking forever. So lock.lock interruptibly can throw interrupted exception. So if we have used synchronized keyword and that thread, let's say in block state, then if we call interrupt on that thread, then that call will do nothing. Okay, so our thread stays blocked, but with this one lock interruptibly, our thread responds to interruption by throwing interrupted exception. Okay, this one is very important. Now next one is non-block lock attempts. Check if lock is available without waiting. Okay, this one will return immediately true or false. And then in finally we can unlock this one. Fairness option. Create a fair lock that grants access in request order, preventing starvation. So reentrant lock, fair lock equals to, we can pass here true. Okay, so that each thread will get this lock in their requested order. This one is first come first served. Okay, so you can do some practice here and we can move forward with our next thing, which is ThreadLocal variables. ThreadLocal provides thread confined variables where each thread has its own independent copy. No synchronization needed because there is no sharing. So if you have created this user instance here, okay, directly like new user, something like that, then each thread will share that instance. Okay, if we run multiple threads on this instance, if we create here this instance with ThreadLocal, then each thread will get its own copy. So we don't need synchronization anywhere, but we have to take care of one very important condition, and that is this one. Current user.remove, we have to call this remove method. This one will prevent memory leaks because let's say when we set any value during one request, and if we are not calling this one, then next request on the same thread sees this one like old value. Okay, so always call this one. Common use cases: user context in web applications, one request, one thread, database connections per thread, date formatters, transaction context. Okay, and we can see here one example. If we use simple date format like without local thread, then this one stores intermediate parsing state in instance fields. Multiple threads using the same instance corrupt each other's results. Then we can use ThreadLocal here. This one is just one example. Memory leak risk in thread pools. Threads are reused. If we don't call this one, then old values persist and can cause memory leaks or incorrect behavior. We have some pitfalls here. Using volatile for compound operations, waiting without a loop. Okay, always use while, forgetting to unlock. This one is very important. Nested locks in inconsistent order. When acquiring multiple locks, always use the same order. Okay. Now we have quick summary and we can move forward with our next chapter, which is concurrent collections.